Okie dokie. Hey, how's it going? We're going to be talking about the ideal gas law today as we do a little science walk and talk. So the thing you got to understand is that I have a favorite theory or formula or whatever you want to call it. And it's the ideal gas law. I guess you could say it's kind of ideal for me. And the ideal gas law is PV equals nRT. So pressure multiplied by volume. So the product of pressure and volume is equal to N. That's the mole or number of atoms, or generally speaking, the amount of stuff times the temperature, that's the T, and the R is the ideal gas constant. It's just a factor that keeps those two numbers equal. So, I could say, for example, pi is just a factor. It tells you that 3.14 times the diameter of the circle gives you the circumference. There's a relationship. And so what is the relationship? The relationship is between the amount of stuff and the temperature of that stuff. You're going to multiply that by or equal that to, I should say, the volume times the pressure. So PV, pressure times volume, equals nRT, but we're just going to throw the R out because that's just a factor. So pressure times volume more or less equals the amount of stuff, the number of moles, N, times the temperature. So question, what's going to happen if you change the temperature? Well, if you don't do anything else, you're going to have to either change the volume or change the pressure. And that's basically how a pressure cooker works, right? In fact, the reason why a pressure cooker works is because of the ideal gas law. Or the principles in the ideal gas law are what allow a pressure cooker to work. So, PV equals nRT. What does that mean to us? Well, think about it this way. We can really understand a lot of things in the world from this, starting with one of my personal favorites, the weather, right? So, you have areas of high pressure, and you have areas of low pressure. Generally speaking, we associate high pressure with clear air. We associate it with nice weather. Low pressure, we associate that with rain, crummy weather. But let's come back to it. If I raise the T, we have the same amount of stuff in our atmosphere. We're not going to have more stuff in the atmosphere. Can I make the atmosphere bigger? No. So what generally happens as we increase our T, our temperature? Well, we increase our pressure. It's the only thing that can change. So if you think about it in terms of the weather, remember this, we are not water-dwelling creatures. But don't get it twisted, we're not land-dwelling creatures either. What we are air-dwelling creatures. We live inside of gas. And in fact, there's gas all around me right here. It's the atmosphere. So we're gas-dwelling creatures, we live inside of gas. And the ideal gas law helps us to understand how that gas works. And remember that? PV equals nRT if you get nothing else out of this, except you get a nice walk. So, first thing you got to know about the ideal gas law is that unlike other laws, it doesn't have a particular person associated with it. And that's because the ideal gas law is actually a combination of 4 different laws. What are those 4 different laws? I'm glad you asked me that question. Boyle's law, and that tells you that if the amount of gas and temperature are kept constant, that pressure and volume are inversely related. Another way of saying that would be that we increase the volume, we decrease the pressure. If we increase the pressure, we decrease the volume. We squish it in. So that was Boyle's law. And I thought it was that a watch pot never boils, but I guess that's a different Boyle's law. Then we have Charles' law. And that tells us that if we have gas at a constant pressure, the volume is proportional to the temperature. So here's the thing. If you keep the temperature the same, the volume's going to remain the same if you keep the pressure the same. But if you raise the temperature, something's got to give between the volume and the pressure. If you raise the temperature, keep the pressure the same, volume's going to increase. You're going to take up more space. If you raise the temperature and keep the volume the same, the pressure is going to increase. And that's what happens inside your pressure cooker, in case you were wondering. Then you have Gay-Lussac's law, which was basically what I just told you, that the pressure is going to be related to the temperature. If you increase the volume, if you keep the volume the same, you increase the temperature, then your pressure is going to shoot up. So it's actually Gay-Lussac who thought of that. And then Avogadro's law. Now, Avogadro's law is going to have something to do with Avogadro's number, which ultimately leads us back to moles, which is the amount of stuff. 6.02 times 10 to the 23 molecules per mole. It's just a way of knowing how much stuff you have. Or should I say particles per mole. And what did he say? At equal temperatures, there's equal volumes of all gases at the same temperature and pressure have the same number of molecules. So that equivalence there, and then the relationships, put all those things together, and you got your ideal gas law, your way of understanding how gases function. So let's come back to those sort of basic principle measurements of a gas, right? Now, the thing about gas is, like, you're never going to be able to measure how high it is, how wide it is, because it's a gas, right? You can measure volume. But as soon as you start to measure volume, don't you start to think gas can do something that a liquid really doesn't do, that a solid really doesn't do, and that's compress. So you can compress a gas. Compress, pressure. So you've got the pressure of the gas. That's something that matters. Matters more than the amount of pressure you put on water. Right? If you think about it, if water changed its volume with pressure, then it would get crushed at the bottom of the ocean. And the ocean would constantly be sinking upon itself, but it doesn't do that. Okay, let's think about temperature. Well, why does temperature matter more for a gas than it does for a solid? Well, because it determines how those particles are going to interact with each other. So if you have a gas, then you put more pressure on it, you're going to lower the volume. But if you raise the temperature, well, let's take a split second here and analyze what is temperature. Like, what is heat? It's a thing. And so what is it? As I say, it's a thing. It's energy. So temperature is a form of energy, specifically a form of energy known as kinetic energy. That means the energy of movement. And what's moving? It's the particles inside of a substance. So, as you heat up a substance, the particles, which are always vibrating, they start to move and vibrate faster. If you give them enough energy, they can overcome the forces that keep them held together tightly in a solid. They can float around each other as a liquid. If you keep increasing that energy, they can change state again. They can move from being a liquid to a gas. And now the particles aren't connected to each other at all. There's tons of space in between them. In fact, you can compress them. You could even liquefy a gas. And in fact, at a certain pressure, anything will be a liquid if you compress it enough. If you push it together enough that the particles start to catch onto each other a little bit and become liquidy instead of free-floating particles, which is what a gas is. So what was I saying? Oh yeah. When you're thinking about a gas, you have to imagine that it's something that doesn't have a specific volume. Rather, its volume is going to be lowered when you increase the pressure, or its volume is going to be increased as you raise the temperature. Because if you do that, then the particles have more energy and they crash into each other with more force and a rebound and stronger directionality, which ultimately leads to all of that stuff becoming bigger or taking up more space. Hence your increase in volume. Now, would there possibly be a way of increasing the amount of space that a gas takes up without increasing the temperature or decreasing the pressure? Well, yeah. If you decrease the pressure, you're going to take up more space, but also if you add more stuff at the same standard temperature and pressure, you're going to take up more space. So that's an interesting thing. Now, see if I can tell you a few more interesting things about pressure and volume and just generally the ideal gas law. It's based on a hypothetical ideal gas, in case you didn't realize that. And the reason why it's a hypothetical ideal gas is we assume that the gas particles themselves take up no space, which, like relative to the amount of space in the whole gas, they do, but they still take up space. So they're an ideal gas. And then there is something known as the real gas law, which accounts for the effect of intermolecular forces, like basically how different particles pull on each other and slow each other down, which, as you can imagine, means the temperature would change. Now, the ideal gas law has a number of real-world applications, which I think is pretty cool. One, which I never really thought about, but totally makes sense, is airbags. And the reason why we use the ideal gas law in this case is because airbags are the product of a gas produced by a reaction between these two reactants. Now, the bag is a certain volume. You want to have a certain pressure within the bag to stop someone. So you have to calculate how many N's, how many moles, how much stuff you want to produce. And then use the ideal gas law to calculate whether that will give you the desired pressure and temperature and everything within the bag. Of course, I talked to you about weather forecasting. The ideal gas law is definitely used to help to predict weather forecasting. And it's used in scuba diving because you have to understand that the pressure underwater is going to change the pressure in your tank. And it's also used in cooking. Pressurized cookers is what I talked about. And R is 8.314 joules per mole degree Kelvin. What's that, Dave? Degree Kelvin, what does that mean? Well, that is the absolute temperature scale. And whenever we deal with temperature in the scientific formula, we have to deal with the absolute temperature. What does that mean? That means the temperature where 0 is absolute 0, minus 273 degrees Celsius. And that's because there is a temperature below which you can't go. That's absolute 0. So what we consider 0 in Celsius is, when does water freeze? In Fahrenheit, 0 was just something they figured that's about as cold as it ever is going to get. So that's what they set as 0 in Fahrenheit. They set 100 in Fahrenheit as, well, that's about as hot as it's ever going to get. In Celsius, 100 is the boiling point of water. Now, in the absolute temperature scale, Kelvin, 100 isn't really anything. But 0 is the point at which everything freezes. All matter stops moving. All particles stop vibrating completely. And so just go back to R, that K is the Kelvin scale, because that's what we call the temperature scale when 0 is absolute 0. So you just learned there are 3 temperature scales. There's Celsius, Fahrenheit, and Kelvin. And the most accurate for scientists is Kelvin. And if you want to know what any temperature is in Kelvin, it's actually pretty easy. You just subtract 272, or sorry, my bad, add 273. So 0 degrees is 273 degrees Kelvin. It's pretty warm. That's 0 degrees Celsius, I should say. Now, I could go on and on about this, but I won't. I think I'll just summarize, finish my walk when I get to that busy corner up there. But pressure times volume is equal to the amount of substance, N, the number of moles, times R, the ideal gas constant, times T, the temperature in Kelvin. The ideal gas law. It's a product of 4 different laws, kind of all mashed together. And it allows you to predict the weather and really just all behaviors of gases. And when the ideal gas law isn't accurate enough, we bring in the real gas law, which is way more complicated, but it accounts for the molecules and the forces in between them and gives you a much more accurate reading when you have to be super, super precise. And speaking of being super, super precise, this is precisely where I think I want to end the walk. So, thank you for walking with me in the Walk and Talk Science. Hope you had a nice time. It was a beautiful day today, wasn't it? All right, peace out.